Okay.
Hello, hi everyone. Welcome to the Geoscience and Geoenergy webinar. This is the 109th webinar we have hosted together with Sebastian Geiger. He used to be at Heriot, but now gladly he's at TU Delft, my direct colleague. So we wish you all are doing well, ready for the New Year break and the holiday season. Today we have the pleasure and honor to host our colleague Dr. Annemarie Muntendam-Bos, who is a senior specialist on geohazards at the State Supervision of Mines, known as SODM in the Netherlands, which is the Dutch Safety Authority for Mining Operations. She's also part-time associate professor at TU Delft, the same department as Sebastian and myself are. So she's our colleague as well at Delft on induced seismicity. And Annemarie studies earthquakes caused by human activities, quite a hot and important topic, especially recently, in the subsurface to understand why and how they occur, with the aim to develop strategies to manage their risks. Over the past 15 years, she had a principal role in identifying, understanding, and managing the risk associated to the induced earthquakes in the Groningen gas field, which is the Dutch gas field in the north of the country. She received her PhD in seismology from Utrecht University, and after that also did a 2-year postdoc at Netherlands Institute for Space Research. So from space, she came to underground, Annemar. That's quite interesting. She's today working at SODM after successful also years, about 6 years, also working at TNO, another national lab, research lab that we have in the country. So, Annemarie, without any further ado, I'm going to hand over the stage to you. Before that, I'd like to remind the audience that, like always, we will have the lecture for about half an hour and then followed by discussions and questions. Please do type your questions in the chat box. After that, Sebastian will take them all, like always. Do not wait until end of Annemarie's lecture to post your questions. Please do type them the moment you feel appropriate, because your question will also trigger other questions by the audience as well. And at the end, we will hold a lively discussion session with her as well. So without any further ado, again, Annemarie, we are all very much looking forward to hearing your lecture, and thank you very much for graciously accepting our invitation to give this lecture.
Thank you, Adi. So today I'm going to be talking on maybe a slightly controversial question, saying that could the early termination of the gas extraction from the Groningen gas field due to the induced seismicity problem have been prevented? So basically our question is, could we have avoided stranding 800 billion cubic meters of gas, especially now with the high gas prices that we have around Europe? This is indeed a slightly provoking question to ask, but could we? And how much of an influence could we as scientists have had on that decision? I immediately going to give you my quick answer, which is yes, I think maybe we could have. I think science could have played a crucial role, but not anymore. We are beyond the point of no return, and Groningen will probably become the largest stranded asset that we have in the world. I'll take the next half an hour or so to tell you why I come to this conclusion. But first of all, let me get you a bit more familiar with the Groningen gas field. It's a very large gas field in the north of the Netherlands, which is a small country, for those of you who don't know, between the United Kingdom and Germany in Europe. And the gas field was first discovered more or less by chance on the 22nd of July, when the first well was drilled near Slochteren on a farmer's land, and it discovered gas. It wasn't known how big the gas field was for a very long time, until at about 1963, 1960, sorry, another well was drilled near Delfzijl, and it found exactly the same type of gas and with the same pressures as was found at Slochteren. So they were quite sure that they found one gas field, and initial estimates ranged from 60 to 300 billion cubic meters of gas that would be in place in this gas field. On July 1963, first production started from the field, and at the same time, they started constructing a very big network of pipelines, basically aimed to connect all the Dutch households to the big gas field because it could provide a lot of heat for cooking and heating of the houses and might replace coal, which was up till then used for cooking and heating. For decades, gas production went very smoothly, especially for long times until the large discoveries were made on the Dutch offshores, where gas was found at great extents, and slowly they discovered that maybe these small gas fields could produce a lot of gas as well. At that time, basically in politics, nuclear energy was expected to displace the use of natural gas, and gas had to be sold as quickly as possible. So production from Groningen gas field quickly increased from very little in the 1960s to over 90 billion cubic meters in 1 year in 1975. In the 1970s, with all these small gas fields coming online, they revised the policy. First of all, there was a lot of social resistance to nuclear energy, and we had the first oil crisis, showing how much worth actually natural gas and oil could have. But also, it was realized that the Groningen gas field was much larger than they had originally anticipated, actually 10 times larger. So in 1964, they had a new estimate, which was a stunning 2,800 billion cubic meters of gas, which is currently still the 9th largest gas field in the world. So together with the fact that nuclear energy was being banned, the small field policy was developed. Basically what it says is that they're going to give preference to all the gas from the small gas fields, and Groningen was going to be used as a backup. Just basically postpone the production from Groningen to the future. So Groningen gas production was declining while the small gas fields were producing more and more. And as of about late 1990s, early 2000s, Groningen started to pick up again while the small gas fields started to decline. It was anticipated that Groningen would fill out this function for a long time and then gradually decreasing production in decline up to about 2070. So what went wrong? Well, gas production has some major consequences. First of all, there's of course subsidence. Already in 1963, based on examples such as the Wilmington gas field in the US, first warnings were issued that the production of the Groningen gas field could result in up to a meter of subsidence. Publicly, the operator declined the prediction, but secretly, it made a study and that showed that up to 1.5 meters was actually feasible. But it wasn't until 1972 before this study became public. Over the years, predictions went up and down, varying from 72 centimeters to 30 centimeters, back up to 65 centimeters, finally aiming at about 50 centimeters. Currently, the observed subsidence is about 34 centimeters in the deepest part of the subsidence bowl, and is aimed to be around 60 centimeters at the end of production. But this isn't the main problem. Our main problem really is induced seismicity. Oil and gas exploration has been associated with induced seismicity since the middle of the last century. A most famous but also controversial example is the Gasly gas field in Uzbekistan, where in the mid-70s and 80s, magnitudes as large as 7 were occurring below the gas field. It's still very much debated whether this is due to the gas field or whether it's a tectonic event, but you could say that maybe the stress changes from the gas field have contributed to actually the stress changes on that fault, and it was a triggered event. Other examples are from the Coalinga oil field in the US, and the most famous example in Europe is the induced seismicity in the Lac gas field, which was generated up magnitudes up to 4.3, with over 2,000 events being detected between 1974 and 1997. In Europe, probably the largest induced event was a magnitude 5.5 event in 1951, which was associated to the previously aseismic Cabiaca gas field in the Po Valley of Italy. It's still the only magnitude 5 gas extraction-induced earthquake reported for Europe. But despite these occurrences, The possibility of any earthquake occurring in the Netherlands, including in the Groningen gas field, was considered impossible for a very long time, also by scientists. Hence, the first seismic event that occurred near the town of Asse in 1986 came as a complete surprise. But it should not have been. Already on March 30, 1976, reports were made for a minor event felt near the town of Witteveen, and locals in Groningen recall several events in the mid-1980s. Unfortunately, these events remained undetected as the network at that time was focused on the southeast of the Netherlands, where natural seismicity is often recorded. And there was just one single station, remarkably, at Witteveen. Following the Asse event, a small but dedicated local network with an estimated detection threshold of about 1.7 was installed in the area around the earthquake in 1988. However, still gas production relation between the gas production and the induced seismicity was denied. In 1990, actually, two scientists from MIT concluded in an assessment for the Groningen gas field that induced earthquakes due to gas production were highly unlikely. And if they nevertheless should occur, they would occur on the boundary faults only, and the magnitudes would not be exceeding 3.0. Keep that in mind when you hear for the rest of the story. In contrast to their assessment, the first official seismic event in the Groningen gas field was detected on December 5, 1991, and actually could not be related to any boundary fault at all. It occurred pretty much within the gas field. It was the seventh induced event that was recorded, and all events were magnitudes between 2 and 3. 4 of them were related to a single gas field, the Eleveld gas field. One of them was actually recorded in the northwest of the country near the Middelie gas field, and one was recorded in the Emmer gas field. Now, in response to these events, a first major study plan was instigated by the Dutch government. They investigated the then heavily debated relation between the gas production and induced seismicity. The study contained 2 major parts. First of all, there was a seismological analysis of the earthquake data, and secondly, there was a geomechanical analysis of the Eleveld gas field. Let's look at parts of these studies. So the study was published in November of 1993, and the analysis of the earthquake data then already went up to studying 24 earthquakes. As you can see, much more events have occurred in the Groningen gas field, but also in the Eleveld gas field and in the Roswinkel gas field, there were now more earthquakes occurring. The seismological, based on the first 4 analysis of the largest events in the Eleveld gas field, a first assessment of the focal mechanism was made, and the pattern that they found was consistent with slip on a normal fault. In addition, a Gutenberg-Richter analysis was made and compared to a Gutenberg-Richter analysis of tectonic events in the south of the Netherlands. A Gutenberg-Richter plot is basically comparing the relation between small and larger magnitude events. Based on this analysis, they concluded a couple of things. First of all, they found that the slope of this relationship was actually much steeper than the slope they found for the events in the south of the Netherlands. They also found that this slope was more consistent with induced seismicity observed elsewhere. As you can see, the relation for the induced event starts to deviate, or actually seems to be deviating. And they concluded that it probably went to some kind of asymptote, which is called the magnitude. A first assessment was made of this theoretical maximum magnitude, and they came to the conclusion that that would be about 3.3. Finally, based on this relation, they correlated the local magnitude and the intensity of the events derived from public data. And they concluded that based on this relation that they found that a magnitude 3.3 event would be correlated with an intensity of about 5 to 6, and that this would give minor non-structural damage only to very vulnerable buildings. The geomechanical analysis showed that reactivation of the faults was possible, and in a normal mode direction. The driving mechanisms for this reactivation was the reservoir compaction, which was a result of the gas production. So in 1993, we had established that gas production could result in seismic events, but magnitudes were not expected to exceed 3.3, even under the most unfavorable conditions. And there was only a very small chance of slight damage occurring in a limited area around the epicenter. But then in August and September of 1994, two major events in the Bergermeer gas field occurred, having magnitudes of 3 and 3.2. And then in 1997, a magnitude 3.4 event in the Roswinkel gas field occurred, a magnitude clearly exceeding what was deemed possible. The reanalysis of the data resulted in an increase in the estimate of the maximum magnitude. So in 1997, it went up to 3.7. In 2001, two more earthquakes were induced in the Bergermeer gas field, including one with a magnitude of 3.5, leading to a further increase in the maximum magnitude estimate to 3.9 in 2003. This also meant that the damage that could be incurred was going up. Intensities of 6 with minor structural damage in a wider area had become feasible for these small induced events. So what was happening in Groningen in the meantime? Well, a lot of earthquakes continued to occur. In the first decade, gas rates were relatively low, and event magnitudes did not exceed magnitude 3. However, after 2003, magnitude 3 events started to occur, and in 2006, the first magnitude 3.5 event occurred near Wester Emne. In 2012, the largest event to date occurred. It was located near the town of Huizinge and had a magnitude of 3.6. You can also see in this relation clearly that the cumulative number of events has a deviating trend, also at around 2003. So clearly the rate at which events were occurring is increasing. Spatially, the events started towards the northwest of the gas field and spread out over time towards the south and the southwest. Events with magnitude 3 or higher have all occurred actually in the central northwestern area of the gas field. You would expect that the development of the seismicity in the Groningen gas field would trigger the curiosity of scientists, but remarkably this was not the case at all. The research that was being done in the years after 1994 was very limited. In 1997, Naugaard and Roest published a follow-up study to their geomechanical analysis that was contained in the BOA study. It focused on one of the gas storage fields and the induced seismicity that was observed there. This was followed in 2003 by a PhD thesis from Frans Mulders, whose research was conducted within the same research group at TU Delft and focused on the Bergermeer gas fields and its 4 remarkable magnitude 3 events. In 2004, a larger research was published which contained part of TNO's work on finding parameters that correlate with the occurrence of seismicity, as well as the first seismic hazard analysis, which was published by Van Eck. The report contained a general analysis of all events in the north of the Netherlands and 3 very specific analyses, one for the Bergermeer gas field, one for Roswinkel, and one for Groningen. Remarkably, the model contained separate Gutenberg-Richter analysis and hazard analysis for these 3 fields and for the north of the Netherlands. However, despite the clear observation that these different fields and all the fields together behaved quite differently, both in annual rates as well as the slope of the Gutenberg-Richter, as well as whether or not that would be a maximum magnitude estimate, it was concluded that the maximum magnitude relation and max in the north of the Netherlands would have remained fairly stable since 1998, and the 3.9 was still very much valid. Following the 3.5 event at Wester Emne in 2006, the citizens of Groningen started to question the KNMI analysis for the MMAX. According to the critics, the rate of seismicity was increasing and stronger events occurred more and more often. At the request of the province of Groningen, TNO and Deltares conducted an evaluation. And in 2008, they concluded, and my conclusion is lost behind the picture, which is unfortunate. But basically, they concluded that the analysis from the KNMI was very much valid and that the magnitude 3 events did not change the conclusions. And that, yes, there was an increase in seismicity observed in the seismicity rate, but unfortunately, they thought that that did not influence the analysis at all. And then the Huizinga earthquake occurred. It was the strongest event to date, with a magnitude of 3.6, and the local population experienced the event as nothing they had ever felt before. It felt stronger and lasted much longer, according to those who felt it. People got really worried and frightened. In the months following, SODM conducted its own study, focusing on 2 questions. First of all, is the earthquake hazard in Groningen changing in time? After all, we see this increase in seismicity rate, and we see an increase in the number of magnitude 3 events. Does this mean that the shape of the Gutenberg-Richter has changed? And what does that mean for the maximum magnitude and hazard? And if that is the case, can we mitigate the hazard? We already observed previously a couple of times that the seismicity rate changed. So what we did is basically draw 2 straight lines through the cumulative data and distinguish that we had 2 clear different behaving periods before 2004 and after 2004. And we subsequently plotted the Gutenberg-Richter data for these 2 periods. Clearly, the change in rate again becomes very visible by a shift of these lines upwards. But at the same time, the slopes of the curves are remarkably similar. However, very different conclusions on the MX would be drawn if you deviate the data in this way. For up to 2003, imposing an MX or the analysis results in a maximum magnitude of 3.1. Whereas for the second period, it was concluded that an MX of 3.9 would indeed suffice for the data. But is this truly the case? If you look at the data, do we need a maximum magnitude? Physically, there's a lot of arguments to support that the size of the events is constrained by the fault sizes that are available and the changes in fault orientations. But is it feasible to derive these from the Groningen data by itself? The answer was no. We performed a Monte Carlo analysis on the maximum magnitude for both periods. We constrained the annual cumulative rate as well as the slope and only drew different maximum magnitudes and analyzed the fit to the data. Based on the analysis of 100,000 iterations, we concluded that the data itself has no constraining capacity for the MX. Any analysis with maximum magnitudes between 3.6 and 7 provide just as good as a fit to the data as any other. So what does this mean for a hazard? As you can see when comparing the solid to the dashed lines, imposing a maximum magnitude significantly reduces the probability of events within about half a magnitude point. It's just 2 blocks. Events above the maximum magnitude are theoretically just not possible by definition. So imposing a maximum magnitude very significantly reduces the hazard. As our analysis showed, the maximum magnitude is not constrained by the data. And if you leave out the maximum magnitude, you get the dotted line, and it has a very different hazard from the solid lines. Note that intensities of events with magnitudes 4 to 5 are around 7, meaning that we move from the expectation of only minor damage into the realm where structural damage is expected, and chimneys may collapse, and even partial collapse of buildings is feasible. So we had a completely different risk estimate compared to what we were thinking up till that point. But as I said, we no longer knew how high the hazard was because no efforts had been made to investigate geological or geomechanical bounds on the earthquakes. How large could the earthquakes become based on the size of the faults? We just don't know. Only now, serious studies in this direction are being undertaken, and we get more and more grips on where this ends. But the finding also leads to a second question. Can we mitigate the hazard? Can we somehow buy time to investigate the hazard further and constrain it again? Well, the studies from the mid-1990s showed that the driving mechanism for the stress changes induced seismicity is compaction as a result of poor pressure depletion due to the gas production. Hence, in theory, if the gas production rates are changing, the rate in pressure depletion will be changing, the rate of compaction is changing, the rate of stress changes are being built up is changing, and we will change the seismicity rate. If we take that assumption and we look at if there's a correlation between the gas production and the seismicity, then possibly you can have a relation there. And indeed, we found a good correlation with about a 1-year delay. Thus, by decreasing the annual gas production, we could reduce the seismicity rate temporarily and buy time to better understand the hazard. However, note that we cannot completely mitigate the hazard as stresses continue to accumulate as long as gas production continues, and hence seismicity will continue to occur. It will just be less events in the same time period. So what happened since? Well, first of all, the operator has commenced a major study program. Millions were spent on better understanding and predicting the seismicity, understanding the specific response of the Dutch subsurface and the local site response of very weak shallow topsoils. He even built a full-scale Dutch house on a shake table to test it for its fragility. After initial hesitance and after a record high gas production in 2013, the gas production was reduced. This did initially lead to a reduction of the seismicity. However, the decrease seems to be tapering off, and we don't know exactly why this is, but you can see that the gas depletion has decreased much more than the seismicity has decreased. In 2017, a very large research program called DeepNL was established with a specific aim to improve the fundamental understanding of the deep dynamics of the deep subsurface. Its total budget is well over 23 million, and it will run until 2025. But really, it has come too late. In 2018, the government decided to consistently start reducing the production from the Groningen gas field with the aim to shut in the field completely in 2030. But over the following years, the shut-in date has moved forward and is now set at October 2023 or October 24 at the latest. So why did the government decide to terminate production? Basically, because the social license to operate was lost. This is partly due to the continuing occurrence of the larger magnitude events, but mainly to the slow reimbursement and repairs of damages. New earthquakes causing more damage were occurring much quicker than they could repair the damage, and therefore damage upon damage was induced in a lot of buildings. Furthermore, in 2013, the emphasis for mitigating the risk posed by the seismicity was put on strengthening of houses. The idea was that we could just strengthen the weak houses, production could continue as usual. But the strengthening operation turned out to be huge. It concerns tens of thousands of houses. Whole neighborhoods were being torn down and completely redeveloped. People are often waiting for years to hear if their houses is safe or need strengthening. In the meantime, they live an uncertain life and are afraid of what may happen when the next earthquake strikes. Currently, the aim of the program is to have finalized the operation by 2028, but more realistic estimates think that it would be more likely to be 2035, over a decade after production is aimed to be terminated. Consequently, the people of Groningen just do not want to deal with the earthquakes anymore. They've come to protests, and they had significantly opposed the gas production. And the government responded. And so I return to my original question. Yes, I think we quite possibly could have avoided terminating the gas production. Think of the amount of knowledge we could have gained if we had invested more in research after the confirmation of the causal relation. How much more fundamental knowledge of the dynamics of the deep subsurface under the influence of human interventions could we have gained already back then? Why did we wait and start only in 2014 and 2017 with the new research programs? Some will say that the amount of data was too limited and that uncertainties were big, but that should not be an excuse to not study a phenomenon. Deal with the uncertainties, be honest about ambiguities and inconclusiveness, and continue your efforts. And always remain critical of assumptions. Others will say that there was no funding for research on induced seismicity at that time. Personally, I do not think that that should be an excuse. It may take more effort and more popular topics, and you may need to fight harder, but there's always a way. So what about now? Even with the current crash crisis, I don't see a light at the end of the tunnel for Groningen. Possibly options such as pressure stabilization are still in the early investigation stages. The research comes too late, and more importantly, we cannot regain the social license to operate. It is lost. Thank you.
Very much,
So I
Annemarie,
give.
for this extremely informative and quite engaging talk. We are thinking about what could have been done in the past and learning also from our experiences. I see already plenty questions posted, so I give it to Sebastian, and especially I am looking forward to see how good Dutch of Sebastian is, because one question is actually posted in Dutch. So
It's a comment, not a question. So I'm going to, in the for our audience and for the native Dutch speakers, I'm going to translate it to English rather than butchering the Dutch. Let's start with a question from Bill Rossen. He says, a very interesting talk. You mentioned the study at MIT discounting any chance of a seismic event. Is there any reason why we can see now why they concluded this incorrectly? Who funded the study?
The study was, I'm not quite sure who funded it. I know that it was related to the operator, and it was done basically with the aim to give more insights in the subsidence predictions that were going up and down and up and down. And as a side note, they also addressed induced seismicity. So it was not the main topic of the report, but they did address it with this conclusion.
Okay, thank you. And then we have a question, from Herminio. It says, thank you for the very interesting talk. Magnitudes of 3.6 don't look too high. Why is it that such a low value can have large-scale consequences to lead the government to shut down the field?
Yeah, that's a very good question. Basically, it is because we are a very aseismic country. So the country is not used to any seismicity, which makes it more prone to be worried when seismicity does strike. But also we have very weak topsoils. So there's a very large site response effect, which makes this events felt much more strongly than you would expect for a 3.6 event, which is also further enhanced by the fact that these events only occur at 3 kilometers depth. So they're very shallow. And then with this large site response effect, we actually have quite significant ground motions. And that's what causes the worry for the people. So they are felt more extensively than a normal 3.6 you would expect in, for instance, the United States or somewhere else. But also because you're not used to it, you feel each one. People are even feeling a 1.5 at the moment. So when you get reports already on the internet, on Twitter, from a 1.5, well before I get a notification from the KNMI, which is quite remarkable.
I think there are anecdotally, just because you mentioned these very low earthquakes, that with the smartphones and the acceleration sensors, someone told me there are apps these days where the people actually also do have essentially their in-house seismometers and measure things it's more difficult to actually feel as human beings.
Yes,
Hermine,
I actually know that there's a few people that built their own seismometers and have them in their basements.
Hermine has a second question, and it's a question I would have asked myself as well. Is there a way we could re-inject other gases such as nitrogen to repressurize the feed and reverse the problem, or if pressure management early on could have reduced the risk of subsidence and induced seismicity?
Definitely a very good question. And yes, if we would have done this in a very early stage, then probably we could have avoided induced seismicity, because we do see that we need a certain amount of pressure depletion before the faults are stressed to the extent that seismicity starts to occur. So if we would have prevented the depletion at all in a very early stage, or have limited to like 50 bars, probably we would not have had the problem. But on the other hand, we are way further now. And at the moment, we have to be honest, it's a huge gas field. So it requires huge amounts of gas. If you're producing 90 billion cubes of gas, or in the highlights in the 2013, it was 50 cubic meters of gas. You have to re-inject the same amounts. You have to make that amount of nitrogen or CO2 or something that you want to re-inject, which takes huge factories. I think they investigated in 2014 it would take 3 of the largest nitrogen factories that were currently out there, and the largest one was in Mexico. So it would take 3 of them just to make the amount of gas that was required. But also you need to build the whole infrastructure, get the injection wells in place and everything. And quite honestly, we know also that injection can give induced seismicity. So with these faults already being so vulnerable and so susceptible for induced seismicity, it's really a big question on whether or not this would mitigate the problem. So we think that it's very worthwhile investigating. We have been saying that from the start. Unfortunately, these studies have started only in the DeepNL program. They are very promising, but they just come too late. By the time we're now starting, even if we made the decision today, it wouldn't be placed for another decade. So it's just comes too late.
You mentioned coming too late. Even Buntic has a really interesting question. So let's assume we can reverse time. And first of all, thank you for the interesting presentation. Let's say induced seismicity was understood in time. We could have reversed time and come with the knowledge we have today and go back to the past. Could there have been any actions to prevent induced seismicity for the future? You just mentioned the big challenges, actually repressurizing the reservoir. Is there anything else we could have done?
It's a good question. I think we are still lacking too much of our knowledge to really know whether or not we could have done things differently. We really lack still the fundamental understanding. We know the processes that are driving them, but exactly how they respond to rate changes, how they might respond to pressure equilibration, to other things that we could have done. We are still at the verge of just starting to understand these things. So I think really I can't give the answer. Maybe that we couldn't have done anything and it would still have ended. But maybe we could have operated the field differently. There's a lot of things that you can think of that could have maybe helped if we had studied them in an early stage.
Just, I'm going to sneak in a quick question there myself. You showed the decline in production, but that the seismicity didn't decline as fast as production declined. And I remember seeing some data from the Basel-induced earthquake, the Basel geothermal operation, in very different geological setting and fracture production. But they had this traffic light system. The moment they saw some seismic events, they shut in the injection. But then the biggest events and the ongoing seismicity happened actually after the shut-in of the wells. So is there something we just don't quite understand, even in terms of operating the fields, if seismic events continue well after we reduced production, reduced injection, try to manage the pressures of the subsurface?
Yeah, well, actually, for induced seismicity due to injection, it's quite common that the largest event occurs after shut-in. And that's why these traffic lights can work. You can see a buildup of seismicity, and then you know that you, at a certain point, have to shut in because you have this trailing effect. And we know that the magnitudes increase after you stop, just because of the pressures being equilibrated or diffusing into the field and triggering larger fault sections. And I think that's the main difference with gas production, is that gas production works more as a tank. So you're reducing the pressure along the whole fault. So you're stressing the whole fault at once. But with injection, you're injecting in one well and it will slowly deviate outwards. And you start to, when you hit a fault, you will start with a small section of the fault and it will become larger. So your seismicity will start to increase. Whereas, for instance, with the Bergermeer field, you can get a magnitude 3 out of the blue for gas production. So that's really, I think, a very fundamental difference between production-induced seismicity and injection-induced seismicity.
Thank you. So you mentioned faults. We have a question here from Saeed Harati, and the questions are coming in at a really high rate at the moment. Very interesting. Did you find any relationship between the type of the field trap structure and the induced seismicity? Have you recorded any earthquakes from the originally unfaulted formation?
No. So we do know that when it's a dip closure, those fields are not seismically active. So you need faults for seismicity to occur. We know that for sure. We also predominantly seem to see seismicity in fields that have internal faults. So it's not occurring, it doesn't seem to be occurring on the boundary faults, but really within the field where you have depletion on both sides of the fault. So the fault is really stressed on both sides. And what we know is that fault offset seems to be doing quite a big, is a big influence on whether or not seismicity occurs, but also how big the seismicity can be. But this is also still very much under investigation. So we're really looking into this. But we have like 30 gas fields in the Netherlands that are seismically active and hundreds that are not. And we're still trying to completely figure out why those that are seismically active are active and why others that looked comparable are not. So that it is really, we don't have all the information yet.
Great, thank you. And your answers were a super segue into the next two questions. So if a question from Priyanka Agarwal, and was, we also have gas fields which don't show signs of major seismic activities. Were there any precursors for the seismic activities in Groningen which got aggravated due to gas production? So was there anything, the subsurface already rumbling, or does it really came out of the blue?
Well, it came out of the blue because we had no sensors there. So we don't know.
We don't know.
Like I said, we had reports as early as 1976 that actually made it into the newspapers. And we have several reports from the 1980s, events in 1980, events in 1984, that have been documented. If you speak to locals, they will tell you that they had events in the 80s, but nothing was recorded because we just didn't have a network there. So unfortunately, we don't know.
And Kishan asked a question, says, thank you for the talk. Considering the outcome of Groningen, can we identify such fields across the world? We could start in the Netherlands, to educate the operators and public already, or is every field different and we need different research?
I do think the fields are different. They're different in sizes, they're different in the type of faults, the orientations of the faults in the stress fields and things like that. But I do think there are analyses now out there that can give you a first estimation on whether or not you can get seismicity. Like I said, fault offset seems to be playing an important role. But yeah, we don't have all the answers yet either. So yes, there are ways to give you a first identification, but it's not a certainty that seismicity will occur or that it will not occur. And we're trying to gain more information on that in ongoing research, but unfortunately, we're not there yet.
Thank you. We have a question then from Willemijn, and she also says, thank you for this interesting presentation. Do you think we learned enough about these Dutch gas fields now to use part of them safely for other applications, such as hydrogen and CO2 storage, which are big topics, of course?
Yes, I think we know quite a bit from them to be able to give a good estimate of what we think might be induced in those gas fields. I do think it's a good decision that for now we do it only offshore, and we can properly study them and see what is happening. Of course, we know from other gas fields that have been filled with CO2 that there is seismic activity there as well. So we really want to get a proper feeling for how the Dutch subsurface will respond to that. And also offshore, there's no people living on top of it. So there is not the big problem with houses being damaged and the problems that are associated with that. You just have your own installations to worry about, which makes it slightly, from a societal point of view, more acceptable.
You mentioned the damage to the houses, and you have a slightly more civil engineering, building engineering question from Jesse Frederick. Would the strengthening program have been this big with tens of thousands of houses if the building codes had been using the most recent insights in seismic hazards?
I think maybe it would have been different if we had a building code for seismicity at all in the Netherlands, which we didn't. I don't think we even have now. We have the building code now that basically for Groningen is determining how far the house is needed to be strengthened. But you also have to take into account, in the picture I showed, there's a very old farmhouse that was already being shut down with all the gates. But that those farmhouses date back a couple of 100 years. So houses in the Netherlands are quite old. And these houses, some of them are even still founded on cow skins. So there's no proper foundation on them. There's just cow skins, and the walls have been built on the cow skins. So those are really difficult structures to deal with induced seismicity, and they are never designed to be dealing with induced seismicity at all. So if you would have had those kind of things in place, yes, things would have been different.
We have a question here because you mentioned CO2 injection from Margaret Kuiper. Which gas fields have had earthquakes when CO2 was injected?
I don't know them exactly from the top of my head at the moment. I know they are there. I've seen many major reports on where they made databases for all induced seismicity in the world, and they are in there, but I don't have them at the top of my head at the moment.
How did you happen to know?
No, I don't think there is any. It might be right for CO2. I mean, there are not many operational actually fields. They have other problems. I don't think induced seismicity is one.
Yeah, I think as well. So the CO2 storage side, the traditional ones, there hasn't been. I'm not aware of big issues there either. So if we have most of the questions, I think we have covered all of the questions. A lot of comments from N. Wiley, for example. Thank you for the informative talk. Margaret just came back and said, I don't think there are any either. So we seem to agree here. Priyanka saying, thank you for the very interesting, informative talk. And I just wanted to come back and how do you want me about the comment in Dutch from Hans Roost, who said he has written in 1993 report to BOA that I'm sort of mixing up my German with English and trying to read Dutch, that other gas fields experience more compaction, and hence we have larger magnitudes of earthquakes there. And he also refers to a study from Koopman et al. From Shell in 1986. So I hope I managed that to your satisfaction. So we can take we have perhaps one final question from Helen Dyson. This very interesting talk. You mentioned that a seismic analysis took place. This happened before the operation of the gas field. So for how long did the monitoring to estimate the natural seismic rate? I think you've answered that partially, but maybe Annemarie, you want to comment, add anything to this?
No seismic analysis was made prior to the earthquake or prior to the gas field starting operation. The first assessment was in 2004 by Van Eck et al. And then the operator started doing large hazard assessments as of 2013, 2014, which are updated annually by now. So no, and there was no monitoring for natural seismicity either, because there was no such natural seismicity from any historical records. So the monitoring was really aimed at the south, where there was historical records of seismicity, but the north was really very quiet and nothing was recorded.
Okay, well, there are no further questions coming through. So thank you, Annemarie, for an excellent talk and for taking the time to answer many questions so diligently. Thank you to our audience for some great questions, for facilitating this really interesting discussion. There are other comments coming through. Again, thanking you for your interesting presentation. So Hardy, over to you for some final comments.
And also the audience as well. I'd like to also introduce our next speaker. Will be in 2023, mid-January. We are going to host Marit Sprenkeling from TNO, who will give a talk about societal embeddedness level as a new concept in parallel to technological readiness level, TRL, and see if we want to develop any geoscientific project at what SEL level in contrast to TRL level the society is. So they are trying to quantify how the society is ready to accept a specific geoscientific application. With that, Sebastian and I would like to wish all of you, our audience, the best in the coming vacation period and the new year. We will see you all back in 2023. As you have noticed this year, we had a break in summertime and then came back with monthly based seminars. And next year we are going to have again monthly based webinars. And so please stay tuned to our channel and of course stay happy and healthy and also tuned into our channel. I guess I have passed on my best wishes to everybody. Annemarie, you are our last speaker of 2022. And as I said to you, we keep the most interesting one at the end, so people stay with us through the year. So I pass on to Sebastian for good wishes for the 2023, and then Annemarie, you have the final words also to say as well. And we actually see Jannik Jansen is online here. So he's in Chicago at this moment. So I'm grateful that he is following us online. I hope he's enjoying the massive crowd of AGU. So Sebastian, please.
Yeah, so Jan-Dirk Jansen is the Dean of our faculty. So Jan-Dirk, greetings to Chicago. Annemarie, thank you again for a great talk. As we said, we saved one of the hits to the last of the webinar. It's certainly not meant to be a disrespect to any of our other really excellent speakers. Thank you to the audience for joining us for which has been the third year running of the webinar series. It wouldn't happen without the speakers, without the audience. It's just Hardy and me facilitating it at the end and providing some software solution to do so. And yeah, also from my side, all the best for 2023. Enjoy the holiday season. I hope everyone has a chance to take some time off, see family, relax, rest. And we see you all for then the fourth year of Geoscience and Geoenergy webinars starting 2023. So until then.
Fourth year. I mean, we are getting old, Sebastian.
We do get old, yes.
Annemarie, final words, please.
Well, thank you very much for having me. It was my pleasure to give the presentation, and all the best wishes for everybody for the holiday season and for the new year.
Yeah, everybody in geoscience community, take good break, enjoy, and we come back again in January for another talk. So all the best and goodbye.
See you all in January. Bye-bye.
Bye, everyone.